Section 6.3 of your student journal. Page is this 168, comparing linear and exponential functions. At this point, it should be pretty simple because we've already gone over lines a ton, and even though we just started learning about exponential functions, it's kind of obvious what they look like, how they differ visually, but whatever. Let's just look at these two, 19x plus 5, 19x plus 5. So there you go, a straight line. 3 to the x, and a curved line that just there's definitely an area where it's like pretty flat, but once it starts jumping, it jumps pretty quickly, exponentially, so to speak. Whether the jumps are going upwards or downwards, you guys just see that there's like a very obvious difference in like their shapes, right? We've done analysis in the y values before where you're adding or subtracting by the same number or multiplying or dividing by the same number. And we're just going to do that more in depth in this section. So as a reminder, a linear function is a y equals mx plus b. An exponential function is y equals a times b to the x. So I know it says quadratic, but then it doesn't give you any examples of a quadratic, so what the heck? But in any case, I think we're mostly just focusing on these two anyways. And that's it. So let's get into it. As a and b increase, the average rate of change of an increasing will eventually exceed the average rate of change between x equals a and x equals b of an increasing linear function. So what this is saying is average rate of change. So if you look at this is a linear function. It's going up by however much it's going up by. And if you look at this, it's an exponential function showing growth. It's not going up by much here. This part definitely shows a greater increase in rate of change. But as we move forward, the jumps get way higher, whereas this stays the same. So this is saying that no matter what, that an exponential function eventually always has a greater rate of change. So even if you have a line that's like starting off at like 1 million x plus 1, like it's so big it doesn't even look like a line. In fact, I'll have to change that to 100x plus 1. And then let's see. Oh, plus 1. Jeez. Versus, let's see, at which point does it look linear? 100, yeah, okay, 50x, okay, 40x. So you see that the line is increasing much faster. But once the blue overtakes it, then the jumps are just so much higher. In fact, to the point where the blue line, the exponential function, looks like it's just going straight up almost. They both look like they're going straight up, almost straight up, but the blue line is clearly going up faster. In exercise 1 and 4, plot the points. Tell whether the points appear to represent a linear function, exponential function, or neither. So again, an exponential function, an exponential function has some sort of curve. A linear function does not. And then neither might be one that you can't tell either. So let's see here. We got to go from -3 to -5. So that means all of our x values can be, but our y values are all positive. So let's go like this. Let's go like this. We could just go by ones. Well, actually, you know what? Change that even more. So this is 1, 2, 3, 4, 5, 6, 7, 8. Okay, -1, 8. -1, 8. We're just going by ones. -1, 8. -5, -1, -2, -3, -4, -5, 8. Negative 4, 4, negative 1, negative 2, negative 3, negative 4, 1, 2, 3, 4. Negative 2, 4, negative 1, negative 2, 1, 2, 3, 4. And negative 3, 2, negative 1, 2, 3, 1, 2. So we have something that looks like this. And the truth is, it's not strictly increasing, it's not strictly decreasing, it's not a straight line. So this one is actually neither. This one is neither. So you guys will just do that for all of these, and you basically just have to do a shape analysis. If it's a line, it's linear. If it looks like one of these guys, it's exponential, and if it's neither, then it's neither. Table of values represents a linear and exponential function. So as a reminder, if it's exponential, we will be able to, if we keep dividing the y values, we will get a constant. So negative 5 divided by negative 2, negative 5 divided by negative 5 divided by negative 2, 2.5. So when I divide negative 2 and positive 1, I expect to get 2.5. So negative 2 divided by 1. That's negative 2. So it's definitely not exponential. And if we look at this, 7 to 4 minus 3, 4 to 1 minus 3, 1 to, you're subtracting by the same amount, so it's linear. Uh, 72 divided by 12, 72 divided by 12 is 6. 12 divided by 2 is 6. 2 divided by 1/3 is 6. Oh, would you look at that? We're multiplying by 6. Exponential. Okay, the data represents a linear or an exponential function, then write the function. So again, if you can't, if it makes a lot more sense, I would make a little table like this, go x and y. Negative 2, so this is x and y. And we're supposed to go in, go in ascending order. Negative 1, 0, 1, 2, negative 4, negative 1, 2, 5, 8. So do the same thing that you did for 5 and 6 on these tables. So you're just testing if it's addition or subtraction or multiplication, really. Okay. So next, a person invests $1,000 into an account that earns compound interest. The table shows the amount in the account after t in time years has passed. Tell whether the data can be modeled by a linear exponential function. Here, you add by 50. Here, you add by 52.5. Are those the same? No. Oh my gosh, by process of elimination, it must be exponential function. If it was linear, the increase would be a constant plus 50 or something like that. Okay guys, that's it for section, I don't even remember what section, I think it's 6.3, comparing linear versus exponential. If you have any questions, ask your teacher or let me know.